So in this case, then if you have pu by puz equal to 0.2 to 0.8, the value of alpha n will vary linearly from 1 to 2, because alpha n is related to pu by puz, and the values are given here that they are between 1 to 2. For values less than 0.2, alpha n is 1, and for values greater than 0.8, alpha n is taken as 2. So that's the value of alpha n that you can use here. In order to check, this is a check whether your design is safe or not, for combined axial and biaxial bending. Now, in this case, in our case right now, we only have uniaxial bending. So you do not need to go for this check. Right now, you can say that this will be equal to 1 already. So in that case, because mu right now this does not apply, so this overall has to be less than 1. Now how that is done, there is a very easy method of doing this, that you have to follow the SP16. Now in SP16, what do you do? Now first of all, what you do, you calculate these values, pu by fck bd. Let's calculate these values. Now we are moving towards check for second case, case B. This is a check that we are going to do for case B, where we are getting eccentricity of 62.5. We have to check whether it's safe or not. So your PU is 1.5 times 2000. That's 3000 kilonewton. Now your PU by FCK BD would be Are you clear what I'm doing, trying to do here? What is your PU? Yes, it's your ultimate load that is acting on the section. Just a minute, I have where did it go? Yes. Now your PU is 3000 into 1000 divided by FCK. How much is our FCK? 30 Newton per mm square. Then you have B cross D. B is 350 and your D is 600. Is it B 300? Just a minute. You have B is 600. B would be 600. This is B. B is 600 and D is 350. Then this would be equal to 0.47, 0.48. This is equal to 0.48. Then you have another, what is your value of mu now? For second case, it's 125 kilonewton meter. It would be 125 into what's given. This is moment from the beam, you have to multiply it by 1.5 such that it becomes the ultimate. So this would be 125 into 1.5. It's 187.5. Then mu by fck bd square, that's what we have to get. Mu by fck bd square would be equal to 187.5 10 raised power 6, and this would be divided by fck is 30, b is 600 in this case, then d is 350 square. So how much would this be? This would be 187 30 divided by 600 by 350 divided by 350. So this is 0.085. Now if you check on what you have to check, PU by FCK is 0.48, 0.48 to 0.085. 0.48 is somewhere here. This is 0.5, so this is 0.48 here. To 0.085. 0.1 is here, 0.08 would be here. The interaction between these two is happening somewhere near to this curve. This curve. What is this curve? This is 0.02, this is 0.04, then you have 0.06. So the interaction is happening close to 0.06. Now, this is P by FCK is equal to 0.06. So thereby, your P by FCK, where P is the percentage of steel, is 0.0, 0.06. It's equal to 0.06. Now P is percentage of steel that you are. Now, how do you calculate the percentage of steel? It's AST by BD. We can say BD here in this case. Now that's 0.06. That's into FCK. FCK is 30. So your P here is 0.06 into FCK. That's 30. So that comes out to be 0.06 into 30. That's 1.8 percent. So this is percent. So this will be multiplied by 100 here. AST by BD into 100 because this is in percent. Thereby your AST now would be 100 into 1.8 into B. B is 600 into D. D is 350. So that would be 100 into 1.8 into 600 into 350. That's this much amount, 378. 378 00 000. This is an mm square. That's the amount of steel that you actually will have to provide in this case, which you require for this case of loading. Now this is as per SP16 charts. Now they themselves deal with the idea of whether eccentricity is being maintained or not. How? Now these charts, they are, if you have a look at these charts, now these charts have rings. Now these rings, what do they resemble? They actually resemble the amount of eccentricity. If your strength is of the sample is below this, for example, now this is the curve that resembles the maximum limit to which this can go, to which you can go for design. So your strength of the sample should be such that you ensure that your pu is always less than this curve. The interaction of pu to mu is less than this curve, then your design will be safe. Now obviously then from here you already are getting the eccentricity. You have already obtained the eccentricity of this, and from these curves you ensure that your design is safe. Now you might have to again check for how much did we provide. We provided, how much did we provide? 4 into ast that we provided, I think, was far less than what is required for when the case is that you have a moment of 125 kilonewton meter. The ast that we provided was 4 into 3.14 divided by 4 into 20 square plus 2 into 3.14 divided by 4 into 16 square, and this was coming out to be 3.14 20, 20, this is 1256. I think you have this. This you are getting as 2059 m square. Into 600 0. Is this right? What here?
वहाँ पे डिवाइड बाय 100 आएगा या इनटू 100 आएगा?
It
सर
has,
नीचे सर.
हाँ, AST has to be divided by 100. That's यही गड़बड़ हुई है. हाँ, मैंने यहाँ पर कंफ्यूज हो गया हूँ मैं while writing this. This is AST. Yes, here. This is AST into 100. Then you have divide by BD. This is BD. So this comes out to be 0.06. That's 1.8 divided by 100 into 600 350. It's 3780. This is 3780 that you're getting. This is not multiplied by 100. This is divided by 100. So, but we have provided 2059. So you need to now actually for this case, when for case 2, you need to again provide a better reinforcement, and that would be, for example, now you can provide 25 bars. So each bar then would be 25 bars. If you provide, then you are getting 3925. Provide 8 number 25 bars for case 2. That's case B here. जिसमें आपको 125 kilonewton meter movement है. Then you will get overall AST provided is 3925 square, which is greater than what you require now, 3780 square. So this is the revision that you have to make for case B. For case 1, for 25 kilonewton meters, this was enough. For case 2, you have to go for the design interaction curve and obtain this revised. So this was all about the determination of the under the uniaxial load, uniaxial eccentric load. If we get in helical reinforcement, when you have a compression member with the helical reinforcement, the strength of compression member with helical reinforcement satisfying the requirements of 39.4.1 shall be taken as 1.05 times. This I have already explained once, that you have to multiply this by 1.05 times. Now, next comes, which is very important in helical reinforcement, there is no other difference in the design of helical reinforcement from the lateral ties other than this, that you have to obtain the volume of the helical reinforcement to the volume of the core. This is known as volumetric ratio. Now, what is a volumetric ratio and why is it important? Its value is less than 0.36 Ag by Ac minus 1 into FCK by Fy. Now, again, we'll get this if we take up an example. Now, the question is same, that you have to design but this time around it's a circular column for a load of 2000 kilonewton. This is dead load plus live load. In this question, what's important now, the helical reinforcement, and in the question it's given to you is at least 10 in diameter. This is the helical reinforcement, its diameter. Now, what is helical reinforcement? It's the transverse reinforcement. जो आप टाइज रेक्टेंगुलर कॉलम में दे रहे थे, यहाँ पर you call it as a helical reinforcement as a spiral. You are providing it as a loop or as a spiral. Now, this will have a pitch. What you need to do is you have to design this column what's given to you is M30 grade concrete and FE 500 steel. Also given to you is that the column is under axial concentric load and is 3.5 meter in, has got an unsupported length of 3.5 meter, has got an unsupported length of 3.5 meter. Now, how would you begin solving this question? First of all, the first thing is you need to fix the dimension of the column. Now, that's not given to you here in this question. I mean, what is given to you is the length of the column, which is 3.5 meter. This is given as 3.5 meter, which is the unsupported length between the ends, between the supports. That's 3.5. So the first thing is, step number 1 is you determine the dimensions of this column. Now we know that you have to at least fix the dimension of the column at 300 mm. So there will be a D. This is D. The D of this column, the diameter of this column is 300 mm. Then we're just assuming that it's 300 mm at this stage for this amount of load. Then step number 2, this is assumption. This is assumption. Now step number 2 is you determine the slenderness ratio of the column. Now in this case, even if it's fixed, it's again an assumption. Then the slenderness ratio would be, that's lambda would be 0.65 into, that's 3500 divided by 300. So because the least dimension is still 300 here in this case, that's 7.58. So it's a short column. Now going to step number 3, we determine the minimum eccentricity for this column. And that minimum eccentricity is either L by 500 plus D by 30. Now that is the unsupported length. L is the unsupported length. This is this plus D is 30 by 30, 300 by 30. That's 10 plus 7, 17 mm, while as least E minimum should be 20 mm. So it has to be at least 20 mm. Then you have to check this, that 0.05 into the D, it should be less than E minimum. This is a check that you have to do. So your 0.05 into D is how much? 15. 15 mm is less than 20 mm. So the design is okay for being considered concentric load. Next, we determine the longitudinal reinforcement. When we are determining the longitudinal reinforcement, now you have to take care here that it's 1.05, which I just explained to you from IS 456. This formula has to be multiplied by, this formula has to be used, which was used in the rectangular column, but you have to multiply it by 1.05 times. The strength has to be taken 1.05 times more here. So this is 0.447 FCK into AG
सर ऊपर जो मिनिमम इसेंट्रिसिटी है वो तो 80 mm आ रही है ना सर आपने लिखा 17 mm
80.
यस सर ये मिनिमम एल 3500 डिवाइडेड बाय 50 वो 70 आएगा
500.
प्लस 10
There is 500 at the bottom. This is 500. While writing here, there's always an error. This is 500. So 0.447, not 0.447. This is just 0.4. You have to take 0.4 FCK into AG. Then you have ASC into 0.67 into FY minus 0.4 into FCK. This is the formula. Now your PU here in this question is given to you. It will be 2000 into 1.5. So it's 2000. The ultimate load is 2000 into 1.5 into 10 raised power 3 in terms of Newton will be equal to 1.05 times 0.4 into 30 into AG. Here now is 3.14 divided by 4 into 300. That's 235.5 is your gross area of the circle, of the circular column. Plus, you have here another bracket. ASC is what you need to determine, 0.67 into 500 minus 0.4 into 30. So ASC now you have to determine. That would be 300,000 is equal to 0.300,000 0.67 into 500, that's 335. 1.05, that's 351. 75 minus 4 into 30 into 1.05, that's 12.6. 351.75. That's just 339.15 into ASC. 3000. 67.3. 7032.7 is 339.157. That's coming out to be ASC is 8836. Same issue is happening while we are designing the 71 mm square. Now we know that a max has to be 4% of ASC by BD. That's 4% of B cross D. Now here, not B cross D here, it's 3.14 by 4 into 300 into 300. That's 706. So it will naturally come to be, I think it's less. It's coming to be 2826. So you need to increase the size of the column now. You need to increase the size of the column. Now, that's a question for you, all of you, that what you will do before we proceed to the how to design the transverse reinforcement of this. This is an assignment for you that you will redesign this for at 500 mm dia. You will redesign the same at 500 mm dia such that I know the values of ASC the next time we meet